Okay, so we can get started. The second part of the makeup lecture. So now we're going to cover the next topic, which is on backtracking search. And I will put these slides on the course web page later today. Okay, so what's the idea of this work is basically to deal with what's called constraint satisfaction problem. We discussed this a little bit at the end of the previous hour when we were talking about problems where you want to find a solution, but you don't care what path you follow to get there. So, so one thing to note about the search algorithm that we looked at so far is that the states, the only thing you can do with a state is to check whether it's a goal state. Okay, and also you can test whether two states are equal or not. Okay, but so it doesn't have the notion of that there's a set of state variables or state features that have different values, maybe a different domain for. It doesn't, so a state is like an atomic object, okay? So you cannot try to analyze different aspects of the state. So this means that it's quite difficult to represent information that really is problem specific, okay? I mean, the search algorithm cannot take advantage of any of that. One way to try to get better search techniques is to say, well, we're going to assume that we use a quite simple, quite general way of representing the state. Okay, and basically one class of such a problem is called constraint satisfaction problem. Okay, and once you make these assumptions about that you have a constraint satisfaction problem, so the state must be represented in a particular way, then we can get more efficient search algorithms. So basically, in constraint satisfaction problem, we're going to assume that the problem is represented as a vector of feature values. Okay, so you have a certain number of features, say k. These are kind of like variables. Okay, each feature can be set to a single value. And each feature has a particular domain of values that you can choose from. Okay? So you might have a feature called height, where there's 3 possible values, short, average, tall. Another one which is weight, light, average, heavy. So 3 possible values. And so in a constraint satisfaction problem, basically what you have to do is to search over the set of values for the features so that you choose some values for the feature that satisfy certain conditions, certain constraints. Here's the first example. So I don't know if you know the puzzle Sudoku. Okay, basically you have a 9 by 9 sort of grid, So essentially, there's 9 subsquares of 9 boxes, and some of them already have numbers in them, and you have to fill in the remaining one so that you satisfy certain constraint. So basically, there's 81 squares, okay, 9 by 9, and you can put a value. Some cells will already be fixed, and you have to fill in the other one. So basically, you can think of this, if you want to model it as a constraint satisfaction problem, as a problem with 81 variable, 81 features. And what values can you put? You have to put a number between 1 and 9. Okay. So there's some cells that are already filled in. So those, we already know what value. They can only take one value, the one that's given. For the other cells, you choose the value. So you can choose any value from 1 to 9. So the domain is basically 1 to 9 for the cells that are not predefined, and just to give a single value for the ones that are already filled in. Now, a solution is an assignment of a value from its domain to every cell that satisfies the following constraint. So the first constraint is that no cell in the same column can have the same value. Okay, so here in column 1, you got to have all the 9 numbers, in different places, 1 to 9. In the first row, you got to have all the 9 numbers in the first row. Okay. Also, so that's the second constraint. No cell in the same row can have the same value. And then also, there's another constraint, is that no cell in the same subsquare can have the same value. So really, here you have 9 subsquares. Okay, so this 1, 2, 3, 4, 5, 6, 7, 8, 9. These are subsquares. Again, all the 9 cells in those must have different values. Okay. So often you see people playing this on the subway or on. Another example. So scheduling, say exam scheduling. Okay. So we want to schedule a time and space for every final exam, so that no student has to take more than one final exam at the same time. The space allocated can only be allocated to one exam, and the space is large enough to accommodate all the students taking that exam. So how do we model this? Well, one simple way would be to say, well, we have I final exam, or M final exam. Okay, so M courses, if you want. And we have one variable for the time slot for that exam. Okay. So here, to make it simple, we could have, say, from Monday morning to Friday afternoon. Okay, so 10 values. But of course, this could be generalized. And then we need to decide, assign a space. So for each of the M exams, we have another variable that says which room we're going to use. Okay, which space. And so now the domain for an exam, say I, it might depend on the number of students that are in that class. So you need a big enough room. So certain exams might have a set of rooms and possible assignments, and other exams might have a different set of rooms that can be values for that exam. And so to solve this problem, basically we want to find an assignment of values to the variable, so a time for the exam and a room for each exam. And here are the constraints. So for every 2 exams, such that there's a student that is taking both of these, they have to be at different times. Okay? And then for every pair of finals, then if they're in the same space, okay, then they cannot be at the same time. So either they're in different spaces or they're in different times. Okay? So these are 2 examples of problems represented as a constraint satisfaction problem. So generally, a constraint satisfaction problem, or people say a CSP, it consists of a set of variables. For each variable, a domain of possible value. Okay? And then a set of constraints. So, in general, to get a solution, each variable can be assigned any value from its domain. Okay? And now the constraint, basically, each constraint has a scope, the set of variables that are involved in that constraint. Okay? So, for example, we'll see some of the examples how that works. And a constraint, so here you might have a constraint on variable v1, v2, and v4. This is basically like a Boolean function. You fill in the variable, it returns true or false. If it returns true, it means the constraint is satisfied. If it returns false, it means the constraint is violated. Okay? Yep. And now we can say that the solution to a constraint satisfaction problem is an assignment of a value to all of the variables such that every constraint is satisfied. Every constraint returns true. Okay? So, for example, for the scheduling, it would mean that we've chosen a time and a room for every exam such that, basically no student will have to take 2 exams at the same time, and they all have rooms that are big enough, and a room is not used for 2 exams at the same time. So it should be something feasible to you. So what are the constraints? Well, for Sudoku, basically, so you have, 81 variables. We can use, a pair of indices, row and column, and if we name the row and the column from 1 to 9, then this means we have variable 1, 1 to variable 9, 9. The domain is basically, as we said, it's basically the set of integers from 1 to 9 for all the empty cells, and basically a set of 1 value for the fixed one. Okay. Then you have, for each row, you have a constraint involving all the variables corresponding to cell in that row. So this is for the first row all the way to the 9th row. For the column, it's the same thing. Okay. You have a constraint for column 1 involving all the variables in column 1 and all the way to the 9th column. And then for subsquare, you have 9 subsquares, so you have a constraint that involves the variable, for example, for this one, it's 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3. So these are the variables involved. And what are these constraints? Basically, that all of the values assigned have to be different for all the variables in the constraint. So any assignment to the 9 variables in a constraint is such that each variable has a unique value. If you have an assignment where 2 or more variables have the same value, this violates the constraint. Often these are called basically all diff constraints. I mean, here that's it. Because of the domain, it means that there's only, you have to use all the values too. So every value has to appear. So basically, Sudoku as a CSP has 3 times 9 all diff constraints. The 9 for the rows, 9 for the columns, 9 for the subsquare. Now, one thing to note is that actually if you have an all diff constraint over k variable, you could replace it by constraints not equal constraint over every pair. Okay, the number of those is quite large. It's basically CK2, I think. So I have this somewhere. Yeah, sometimes people write, so C9, here in this example, it's C9 2. So choose 2 from 9. And so this is basically 9 factorial times over 2 factorial times 9 minus 2 factorial. Okay, so this is the number of any Q constraint that you need to replace one of them. Okay, and this is any Q is simply the 2 variables have different values. So this is an example of constraint. Non-binary constraint can often be represented, reduced to a larger number of binary constraints. For the exam scheduling problem, so basically, as we saw, we have 1 time variable for every exam and 1 space variable for every exam. So what are the constraints? Well, basically, for every pair of variables of final exam I and j, such that the student that's in both courses T not equal Ti and Tj. Okay, so how many of those constraints you have depend on exactly what your student population is. Then the other one is basically the one that says that either this is not equal or this is not equal. Okay, for every pair. So here, basically, to m square, you have m square of those. Okay, so if you have 10 exams, you would have 100 of those to say that, for every pair of exam, you cannot, put them in the same room if they're in the same time. So how can we solve this, these kind of constraint satisfaction problems? Well, one popular approach is essentially to use a specialized version of depth-first search to solve these problems. So what are some of the key ideas? Well, basically, here, the order in which you assign the variable does not really matter. You just want to find the assignment. Okay? So basically, you can think of building up a solution by assigning one variable, then assigning another, and so on. Basically, your search space is the space of partial assignment. Okay, where some variables have been assigned and others have not yet been assigned. So as I said, the order does not really matter as long as eventually you have assigned all the variables. And if during the process of building up the assignment, you violate the constraint, then this is not going to lead to a solution. Okay? As soon as you can check that there's some constraint violated, then there's no use continuing with this partial assignment. Okay? So you can immediately reject all possible ways of extending the current assignment. And so basically, this leads to the following algorithm, which is called backtracking search. Okay? So basically, this is basically a recursive algorithm. Okay? So you start at level 0. Now, there's an exit condition, basically. If all variables have been assigned, okay, then print the value of all the variables, and you can return if you or exit. So if you want to exit, you will only get this solution. If you want, you can ask for another solution, and then it has to backtrack to find a different solution. If it's not the case that all variables have been assigned, then you pick some unassigned variable. You remember that at this particular level you assign that variable. Okay, so you have an array of variable, array called variable for a given level, and you have a Boolean array that you remember that now this variable has been assigned, and basically this loop can try different values from the domain of that variable to assign. Okay, so it chooses, it goes through the member of the domain of V, assign that value to that variable. And here there's a flag that's set to true, and then there's a loop over the constraint. Okay, so for each constraint, that V is a variable of that constraint, and all other variables of C are already assigned. If C is falsified, then you change the flag to false. Okay, so you check all the constraints that way. And then when you get here, you only continue if basically no constraint was violated. Okay, if some constraint is violated, then you go back here and you try different assignment for that variable. Okay, so if all the constraints are fine, then you go to the next level, and so here's what the algorithm essentially does. So at the root, okay, level 0, there's no variable assigned yet. Okay. Then at level 1, maybe you choose VI to assign first. So one value in the domain of VI is A. So here you chose to assign the value A. Okay, then maybe here there's no constraint violated, so you can keep going down to assign other variables. Okay, you hope to find down there some full assignment that satisfies all the constraints. Okay. So basically, here we assign VI to B instead, and here C. So if you had just 3 values, A, B, C, in the domain of VI, then your tree would look exactly like that. Okay? And so you build essentially, the backtracking search will go down this tree using a form of depth first search. Okay, so it assigns the first value, then it keeps trying to continue. Now, here, say after doing Vi equal B, it decides to choose Vj, and say for Vj equal 2, there's some constraint violated. Okay, then it doesn't need to look further, because it knows that with Vi equal B and Vj equal 2, there's no way to satisfy all the constraints. There's no point in trying to assign values to the other variable. Okay, so as soon as you have a node where some constraint is violated, basically you don't need to search further for this partial assignment. Any way to complete the assignment will not work. And so you can backtrack and try a different assignment to Vj, or if there's none, you have to go back and say Vi equal B is no good. Try Vi equal something else. So this is the basic algorithm. So now here, there's still some choices to do. So first, there's a choice of which value to assign to a given variable. But even before that, there's a choice of what order you're going to assign the variable. Okay. The variable may have different domains. Some may be very large, some may be very small. Okay? Is it better to assign a variable with a small domain first, or one with a big domain? Can depend. Also, some variables are involved in a lot of constraints, and others may be only one constraint. Okay? So the other thing too to notice is that you don't have to assign the same variables in the same order in every branch. Okay, so here at the root I chose Vi to assign. Okay, but after, if I do Vi equal A, here I could assign Vk next. Here I can assign Vj next. Okay, at this child, and in this one I could assign VW. Okay, so how you fill in the assignment down a branch, it's up to you. So you can try to choose a good order. Okay, so actually in the algorithm, so there's this function which decide which variable to assign. Okay, so different ways of choosing the variable can have a big impact on how quick you're going to, how many nodes you're going to have to expand to find the solution. So as it says, this dynamically chosen variable ordering can really have a huge impact on performance. Let's see how this works on an example. So here we're going to take a smaller example to make it something we can discuss in detail. So another example of a constraint satisfaction problem is n queen. Basically, you want to put n queens on an n by n chessboard so that no queen can attack any other. So basically, how do you model this as a constraint satisfaction problem? Well, we can assume that there's a queen that's going to go on row 1, another one that you can't put them on the same row. So Q1 is going to go on row 1, Q2 is going to go on row 2, and so on. And then we can say that what you can choose is what column the queen on row 1 goes. Okay, so you can say that Vi is the variable for the column of the queen on row I. And its possible values would be, if you have if you have 8 queens, then it would be column sum 1 to 8. Okay, so the domain is 1 to 8 for each for the variable V1 to V8. What are the constraints? Well, the first one is you cannot have two queens in the same column. So for all I and j different, then Vi cannot equal to Vj. And the other one is the diagonal. So the queens cannot be on either diagonal. Otherwise they attack each other. So basically, one way to write this is to say I minus j is not equal to Vi minus Vj. So if this is satisfied, the absolute value. So if this is satisfied, then they will not be on the diagonal, either diagonal. So here's how the search might go. So suppose we want to assign V1 first. Okay. So initially, nothing is assigned. Okay. This is the 4x4 version. So V1, we can choose value 1, 2, 3, or 4. Okay. Suppose we assign it to value 1. Then at the next level, we have to choose another variable, say V2. So here, if we put it there, one constraint is violated, the column constraint. So this is no good. We don't continue. We try a different assignment. If we put it here, the diagonal constraint is violated. So this is no good. So we don't look further. We go back. Here, now, this is good. Okay, this does not violate any constraint. Okay. Doesn't violate column or diagonal. So now we choose another variable to assign, say V3, okay, the position of the queen on the third row. If we put it here, column violation. If we put it here, diagonal violation. If we put it here, column violation again. We put it here, again, diagonal. So none of these can be, so we don't need to consider any possible value for V4. We know right away that this is no good. So now we have to go back and try, the fourth possible value for V2. Okay. So here, if we set, now we can choose there's no constraint violated here. So if we choose for the value for V2, this is bad for a column. This is fine. Now we can look at V4. So if we put V4 here, column violation, column, diagonal, column. So none of these work. Okay? So now we have to backtrack and try a different choice. Here we tried all the choice for this, so we backtrack here, try a different choice here. This is bad, this is bad. Okay? So this means that now none of these work, so we have to go back here. This was a bad choice. Okay, so so if we put the first queen on the second column, then here this will fail. Okay, then if we put the second one here, then there's a way to choose this. Okay, and then first we're going to try V4 here, here, this will work. So now we found the solution. Okay? So the interesting thing to observe here is that, we did the search, but we didn't have to look at all the possible assignments. Okay? I mean, the number of assignments, if you had if you had 4 variables of domain 2, then it would be 2 times 2 times 2 times 2. So 2 to the 4 possible value. But if you have, say, 10 variables of 10, then this would be 10 values, then 10 to the 10. Okay? So the number of possible assignments grows very large, but the point is that to use the constraint to try to avoid looking at most of these assignments. So what kind of constraints do we have? Okay. I mean, if we want to try to analyze a little bit further how this works. So some constraint may involve only a single variable. So we might have a constraint that says x can only be given the value 2. Or y must be greater than 5. Okay? Or you can have, these are unary constraints. You could also have binary constraints over 2 variables. So you might have something that says that x plus y is less than 6. So another thing you can do is to try to understand the problem better is to basically, for your binary constraint, draw a graph that represents, has an edge for every constraint, binary constraint. So here it's called the constraint graph. So you might have a node which is, the nodes are variable and the arc represents binary constraints. So in the 4 queens, basically the constraints are binary, basically not equal for the column for every pair of queen, and for every pair you have the diagonal constraint. Okay, so basically there are edges for every pair of a variable. Another example that's used in the book is basically you want to color the map of Australia. so that neighboring states have different colors. Okay, so in Australia, basically, you have a certain number of states. Okay, so there's South Australia, there's New South Wales, Victoria, there's Queensland, there's the Northern Territory, and Western Australia. And then there's Tasmania. Okay, Tasmania is an island, so you can put it any color. Then you have constraint that neighboring region. So the neighboring region are these. So basically, every variable, if there's an edge between them, they cannot be assigned the same color. So you can use this kind of graph to try to understand better, how setting a variable allows you to check how many constraints. You would rather check the constraint early rather than later. Okay? So here, if you set SA early, you're probably better off because as soon as you set another, you can check that constraint. But if you don't set this early, maybe you set this first, no matter what you choose here, it's not going to make any difference. So you're not really eliminating anything. The game here is eliminating as many assignments as you can as early as possible. And then you might have a higher order constraint, so 3 or more variables. Actually, one can show that we can convert any constraint into a set of binary constraints, but you need to introduce more variables. Okay, so essentially, the variable now, their value would be like tuples for the other, of values for the other. So they will have a large domain. Okay, so what are the problems with this approach? Okay, the simple version that we've seen so far. Well, one problem is that if we've only set these squares, okay, then there's no possible assignment to a value to this variable that's going to work. Okay, because you've already used 3 numbers for the first row here, 3 for this row, and 3 for this column. So this guy no longer have any possible thing you can assign to it. Okay. However, it's still very early in the search. Okay, most variables have not been assigned. In fact, you cannot check this constraint, you cannot check this constraint, you cannot check this constraint because most values have not been set yet. Okay, it's only once all of these have been set that you can check whether it's satisfied or not. So basically, here we have a variable that if we analyze the problem, we can see that there's no possible value for this variable. But in the backtracking search, we won't detect this until all variables for either a row or a column or a subsquare have already been assigned. So basically, we're somewhere up there, but clearly, no matter what you do in the rest, you're going to get, it's all going to fail. Okay? So you have a situation where your partial assignment is already leading, all possible extension violates some constraint, but you don't know yet. And you cannot easily detect that. So one technique that can be used to try to improve the basic algorithm is it's a set of techniques called constraint propagation. Okay, so constraint propagation means that you try to detect cases where there's no extension of the current assignment that will satisfy all the constraints. So you're trying to look ahead from the current partial assignment to see, no, you don't have any violation now, but is it possible to extend it? Is it a dead end nonetheless if you did a little bit of look ahead? Okay, so so basically you're trying to detect obvious, inconsistencies. I mean, it has to be obvious because if it's involves too much analysis, then this is going to slow down the search a lot. I mean, one advantage of this algorithm is that it's very fast. Okay, you just set a variable and you keep going. Okay, there's not a lot of computation involved. You just have to check the constraint, of course, but presumably these are just Boolean functions, so it's fast. So here there's a trade-off. The constraint propagation has to be fast because if it's slow, then if it's time-consuming, then it's going to lower the number of nodes per second that you can process. Okay, so basically you're not going to have any benefit. But if you can do a little bit of analysis, detect an obvious inconsistency, then you can backtrack now rather than try all these possibilities and know you and fail. So so basically, if propagation is slow, then this can slow the search down to the point where there's no benefit to using propagation. So there's a trade-off between searching fewer nodes in the search because you're doing propagation, which is eliminating, node earlier, and having a higher node processing rate because you're doing less reasoning at each node. So one technique a simple technique for doing this is called forward checking. And there you do only a small amount of basically look ahead or propagation. So what you do in forward checking is that when you set the variable, okay, you check not just the constraint that have all their variables filled, but also constraints that have only one variable left. Okay? Only one uninstantiated variable remains. And for that uninstantiated variable, you try all the possible values, and if there's a value that leads to a violation of a constraint, you remove it from the domain of the variable. So you kind of filter the domain. So basically the algorithm is the following. Okay. So the forward checking procedure, so you have a constraint that as all its variable already assigned except for variable x. So now you look at every member of the current domain of x. If assign a value d from the current domain to x, falsify the constraint, then you remove it from the current domain. And then if the current domain becomes empty, then basically this means that now there's no way to continue with the current partial assignment. So you have what's called a domain wipeout. This is a special, condition that you can return. Otherwise, basically, you can continue, but you have eliminated some possible values from the domain. So now the domains, there's one version of the domain that is according to the CSP, the starting CSP, but here you're shrinking the domain according to the assignments you've made so far by doing this forward checking. So this is the full version of the backtracking search that uses forward checking. Okay, so this part is the same as before. So you pick an unassigned variable. You remember that this is the variable for this level. You remember you've assigned it, and then now you choose a value for that variable from the current domain. Okay, so this may have shrunk due to the things you did at the previous level. Okay, and you assign it to v, then you check the constraint that have at most one unassigned variable. Okay, and you check it using this forward checking procedure that we saw before. If it returns DWO, domain wipeout, then you have to try a different value. Otherwise, you go on to another level. One thing you have to do, though, is when you backtrack so after you continue going down the search, if you come back and you have to try a different D for V, then you have to restore the ones that were pruned further down. So let's see how that works for the 4 queens example. You're going to see it makes a big difference. Okay, so you start, nothing has been assigned. Okay, then you try, let's assign Q1 to 1. The first queen of the first row is in the first column. So now you do forward checking. So one constraint is between Q2 and Q1. They cannot be the same. Okay, so this is cannot work. So basically, and this cannot work either. So basically, originally the domain of Q2 was 1, 2, 3, 4, but these now we know that they will violate constraints, so we remove them. So what's left is 3, 4 for Q2. For Q3, you eliminate this and this. For Q4, you eliminate this and this. So we see that all the other variables, right at this level, by setting one value to Q1 equal 1, we are able to shrink the domains of all the other variables by half. Okay? So now for Q2, we cannot choose 1, 2. We just can choose only 3 or 4. If we choose 3, okay, then so we put it there. So this means that now Q, Q3, these two values cannot be used, okay, because they violate. So now you will have a domain wipeout for Q3. So right away, you backtrack. You go and try Q2 equals 4. Okay? So Q2 equals 4, now this will shrink the domain for Q3 to contain only 2, because 4 would be violating a constraint. Okay? So now Q3 has still one possible value, which is 2. So now you can go and assign Q3 to 2. Okay? And here, so now you will have a domain wipeout for 4, because the only remaining possible value was this one, and it's violating a diagonal constraint. Okay? So here you can see that there's a little bit of look ahead. It's kind of like you're looking one down, okay? And you're making decision based on this. And so this prunes a lot of the search that you would have to do. You kind of detect much earlier, okay? So this is what we saw before. And then when you choose Q1 equal 2, then these will be eliminated right away by forward checking. Then here, the only choice is fourth, is this one. So this will eliminate this as well. Okay. And so now Q3 is fourth. There's only one choice. Put it here. This eliminates this. So Q4 is fourth. Okay. So basically, you're doing almost no search here. Okay. Because you only considered very, very few configurations. Like, in this branch, you had no choice. You just went straight to the solution. Okay, so we can see that this is, potentially a very productive way of doing the search. As I mentioned, so when you backtrack from the current assignment, then you have to, when you set the variable, you may prune the domain of some other variable. So if you change your assignment, then you have to undo that. Okay? So that's important. And you may have to keep track of which assignment led to which values being eliminated, so you can undo that when you backtrack. Another thing is, what about heuristics? Okay, so again, here, this was a very simple problem, so we didn't have to do anything smart to choose which variable we would assign first. But if you have many variables, like in Sudoku, for example, then you need to be smart about that. Okay? And if you use forward checking, then you get for free a kind of very powerful heuristic. Okay? The heuristic is basically that the next variable to assign should be the one that has the fewest value in its current domain. Okay? So this was the intuition that I talked about. It's related to basically if the constraint, if the partial assignment you have means that, there's choice of value, allowable value for a variable that remain is very few, it's better to basically set it so that you can, because you won't have many branches, okay? And setting one variable tends to, eliminate choices for a lot of other variables, okay? So and the other thing too is that it's good when your choice becomes fourth, because then you're going straight down to a solution. Okay, so you're trying to get to the point where a variable has only one value left, and so when a variable has only one value left, I mean, what this amounts to is you just propagating the consequence of that choice. So this extracts the most information from the constraint as possible. So if you do this minimum remaining values heuristic to choose which variable to set, you will tend to have trees that have, few branches at the top and maybe bushy things at the end. Okay, and so this means that you will be doing less work. More variable can be instantiated with fewer node search, and you can do also more constraint propagation with the forward checking, and you will get more domain wipeout failures with less work. So here, there's some experimental data. Quite often, backtracking with forward checking is about 100 times faster than without it. Okay, so this small amount of propagation is really worth it. And if you use forward checking with minimum remaining values heuristic, in many cases you get to be 10,000 times faster than plain backtracking search alone. Okay, and on some problems the speed up can be much greater. So this can convert problems that are really not solvable to problems that can be solved, large problems being solved fairly efficiently. Okay, so maybe I will stop here for today, and let's see how much more we have. Actually, I have only 2 more slides for this, so let me try to finish this. So, forward checking is amount to the same thing as let's go. So another form of propagation is to make each constraint or the constraint graph arc consistent. This is also called two consistency. So a constraint that involves 2 variables, cx, y, is consistent if for every value of x there's some value of y that satisfies c. Okay, so this arc consistency can be applied when you have 2 unassigned variables. Okay, forward checking is for 1 unassigned variable. And this can be done to eliminate values from the domain of variables. So say you have this constraint, x greater than y, with the domain for x 1, 5, 11, and for y 3, 8, 15. If you choose x equal 1, there's no value of y such that y is greater, so that 1 is greater than y. So you can basically right away, you can, by analysis, you can eliminate 1 from the domain of x. If similarly for y equals 15, there's no value of x that's greater than 15. So you can eliminate 15 from the domain of y. So you were able to shrink the domain of x and y by doing this analysis. Okay, so clearly, these here, I mean, you didn't try any part assignment. You just says reason about, this is a constraint involving variable with these domains, and some values cannot be used to satisfy the constraint. Okay, and if you do this, say for one constraint, this might shrink the domain of one variable, and then you can look at another constraint, and then some more variables, some more domains may be pruned. Okay, so if you're doing this arc consistency, I mean, basically you repeat the procedure with each constraint until you cannot eliminate any more value from any domain of any variable. You can have a queue that basically stores the constraints that may need to be checked again. And this is basically stronger than forward checking. Basically, forward checking only checks, forward checking is really like one consistency as opposed to two consistency. It checks constraint when there's one variable that's unassigned. This checks constraint when two variables are unassigned. Okay. Finally, there's some example that can show that really, in standard backtracking, you just go back to, if you get an inconsistency, you go back to the most recent choice. Okay? But sometimes this is not the best way to work. Okay? So the standard approach is called chronological backtracking. Okay? So imagine you have this little example. You have a constraint that's on x, y, z that says x not equal to y and z greater than 3. And you have another constraint that says w is even. Okay? Say the domain of x and y is 1 to 5. The domain of z is 3, 4, 5. And the domain of w is from 10 to 99. So say we set x first to say 1. Then we set y first to 1. Then we set w to 10. Okay? And then we try, so we try z equal 3, and by the first constraint, z has to be, x cannot be equal to y. Okay, so when you set z to 3, you will check that constraint and it will fail. When you set it to 4, you will check it, it will fail. When you set it to 5, you check it, it failed. So all the different values of z will fail. So you backtrack, try w equal 11. Okay, and so on. So you will have to do a lot of work to see that choosing x to 1 and y to 1 will not work. Why? Because there's this part in the constraint that will always be false. Okay? So, but the way backtracking does the job here is not smart, because it should be really the constraint fails because of the assignments that are done here. So really, when you have a failure here, there's no point changing the value of w, because w does not even appear in the constraint that's violated. Okay, for sure, changing this will not make this succeed. Okay, so with back jumping, basically you backtrack to the last variable among the set of variables that caused the failure. This is called the conflict set. And so the conflict set of a variable is the set of previously assigned variables that share constraint with V. So here, the conflict set for Z is X and Y. Okay, and so that would, you would go back to changing Y. It can be shown that forward checking actually detects these kinds of things. So basically, this is the simple back jumping. But there are more advanced forms of back jumping. One called conflict-directed back jumping, and so where you manipulate the conflict set. So so you can look at this in the textbook, and so basically I'm going to stop here for this, and next time we'll move on to the next topic. Okay, any questions?
Question.
Yes.
So could you use two separate backtracking search to search X, Y, and W because they are two separate predicates?
Well, here, I mean, you have variables, so X, Y, Z, W, and you have constraints. Okay, so I mean, you might you could. This is a bit of a contrived example because you could have separated this into two different binary constraints. Actually, one binary, one unary. Okay, but this might not always. This was just to illustrate. In general, you can construct similar examples and basically, have this kind of problem where you, trying to find where you need to backtrack to be able to make a difference in the inconsistency that you got. Okay, in general, it's not obvious. Okay. Okay, thank you.